Right, well, as it turns out, I forgot to record the mass spectrometry lesson at school. So, in hindsight, I'm now recording it at home on a tablet, and I'm not very good at using the tablet, so I apologise in advance for any scribbles or any mistakes. But hopefully, we'll get through it, and it will make some sense. Anyway, mass spectrometry is a technique that we've already studied. We studied it last year. We used it last year to determine the mass of isotopes, the percentage abundance of isotopes, so it's not new. We used mass spectrometry last year and became also pretty familiar with all the different components of the mass spectrometer. So just a little bit of revision. The vaporized sample excuse me, is injected into the mass spectrometer, or sometimes, if the sample is a liquid or a volatile solid, it has to go into a chamber called the vaporization chamber. But let's assume that it's already vaporized. So it gets injected into the mass spectrometer. It then goes into the ionization region, and the ionization region, you'll remember, is the region of electron bombardment. So there are electrons moving through this region here, being emitted off this hot coil and being attracted towards the positive plate on the other side of the mass spectrometer. And as they collide with atoms, they can knock electrons from the atom out of the atom. They can continue on towards the plate, but the net effect is the atom now has lost an electron. So the atom is an ion. Ionization. As soon as the ion is produced, it gets accelerated through to these plates, these negatively charged plates, and so that's why this region is called the acceleration region, and there is a little gap there in the plates. Most of the particles hit the plates, but occasionally particles, well, quite often particles come through in a nice, neat, focused beam of ionized particles. They then enter the deflection region, where they're exposed to a perpendicular magnetic field that causes the particle to curve based on its mass charge ratio, MZ ratio. Now, normally the charge is just 1 because only one electron is knocked out, so they curve on the basis of their mass. But occasionally the bombardment causes 2 particles to get knocked out, so they will curve twice as much because they are now doubly charged. As we proceed through to the last section of the mass spectrometer, but we'll just have a closer look at what happens in there. You can see there are 3 beams, the red, the green and the blue. Obviously the red particle is the heaviest because it continues on to the edge, to the outside edge of the mass spectrometer. The blue particle is the lightest because it's deflected most by the magnetic field. The green particle is of intermediate mass, and that continues on to the detection region of the mass spectrometer. At the detection region, you remember that there is a plate that is connected to an electric circuit. So there are electrons in the plate, and as a charged particle, an ion hits that plate, electrons jump onto it to neutralize it, and in turn causing electrons throughout the circuit to jump, so we get an electric current being generated as particles hit that plate. Now the more particles that hit, the stronger the electric current. So in the end, we end up with a graph that shows the number of particles that hit, and the height of the column is an indication of how many particles hit. The different particles have a different mass charge ratio, and the heavier particles obviously are further to the right. So we end up with this graph called a mass spectrum. Now, in this particular option, we're looking at the ability of the mass spectrum to break molecules apart. And what you can see here is this molecule has been injected into the mass spectrometer, and the molecule is bombarded by electrons as well. So electrons can hit that double bond, electrons can hit the oxygen that has a couple of non-bonding pairs, electrons can hit that bond, electrons can hit the bonds between the carbons and the hydrogens. So there are lots of places where electrons can collide with that molecule. And effectively, when it does, it breaks the molecule into pieces. So let's pretend that an electron hit there. Okay, and then so therefore electron bombardment breaks that bond. Now it's quite possible then that if that happens, and let's just remind ourselves of what a bond is. So if we look at a bond between carbon and carbon, there's an electron from one carbon and an electron from the other carbon in the bond. If an electron gets knocked out by bombardment, so let's say that cross gets knocked out, we now have only one electron between those two carbons. And one electron doesn't constitute a bond. So that electron might very well go back to the original carbon, causing the other one to become an ion. Or alternatively, the electron might go to the carbon on the right, causing the carbon on the left to become an ion. So one way or another, when electron bombardment occurs, you produce an ion and you produce a radical. Now the radical stays in the mass spectrometer, but the ion gets accelerated and it comes out. So what you can see here in this graph are the peaks for what we call the fragment ions. Okay? With the exception of this one. Now I'm just going to rub out some of these drawings. Right, so we can see these. This graph shows all the bits that have come through the mass spectrometer as the molecule gets broken into pieces. So let's study some of the bits. This bit on the far right is called the molecular ion peak. So quite likely what's happened to make this ion is one of these non-bonding electrons on the oxygen has been knocked out. No bonds have been broken, and consequently the molecule has come through, and it's just an ion now. So this tells us the molecular mass. The little peak here to the right of that, they're called shadow peaks, and they're usually due to isotopes of hydrogen or isotopes of carbon present in the organic molecule, and they're usually 1 or 2 atomic mass units either side of that molecular ion peak. So really we're just looking at the biggest peak furthest to the right in the graph. That's called the molecular ion peak. The biggest peak of all is called the base peak. So in other words, this is the most common fragment ion, and then all the peaks other than the molecular ion peaks are called fragmentation peaks. So it's the molecule being split into pieces and the fragment ions are coming through. So please just remember that these represent the ions. Okay, and the IB markers will deduct a mark if you don't recognize that these are all ions. They must be ions to come through the mass spectrometer. So just before we advance to the next slide, I just want to highlight one thing about this particular fragment, and that is some of the characteristic numbers. Now, if we say that this to the far right is the entire molecule, and this first big peak to the left is a fragment of the molecule, then the difference is the piece that has been knocked off, or the piece that's been left behind. So we can see here that there is a difference of 15. Now that's the molecular mass of something that has been left behind. And it's not surprising that this molecule does have that magic number in the spectrum. That number 15 is characteristic of a methyl group, and this molecule has quite a few of them. See, so it's no surprise that the base peak is the most common peak, that 83 is the most common peak, because there are lots of ways in which we can knock off something that has a mass of 15 from this molecule. So what we'll later see is the importance of some of these other numbers, and then eventually you'll be able to recognize the numbers quite quickly. Okay, so this is the spectrum for carbon dioxide. So carbon dioxide, as we know, it's CO2. It has two double bonds. So if fragmentation causes that bond to break, you would get an oxygen ion coming off, which would have a mass of 16. And that is evident here in the spectrum. If the double bond breaks and the CO ion comes off, then you can see that we would end up with a fragment that has a mass of 28. And again, that's present in the spectrum. This is the molecular ion peak, which is the mass of the carbon dioxide ion. And so the mass spectrum of carbon dioxide is fairly straightforward. Right, this is propane. Let's see if we can make some sense of this. Propane, CH3, CH2, 2, CH3. So if molecular bombardment or electron bombardment occurs there, we would knock off a methyl fragment which has a weight of 15. Or if molecular electron bombardment occurs there, we would knock off a methyl fragment again, which has a weight of 15. And we can see that 15 is a common spike. So this would represent a CH3 ion that has come through. And from the structure we can see how that's possible. Alternatively, if the CH3 stays behind, then we could get, I'll go for a different colour, yellow, we could get this fragment come out, which is an ethyl fragment, C2H5 plus, and that has another characteristic magic number of 29, and 29 is evident here in the spectrum as well. So just these two key numbers, 15 and 29, gives us a clue as to what is present in the original molecule, C2H5 plus. So I mustn't forget that they're ions. And propane, that is its molecular weight. 44 is its molecular weight. So that's the molecular ion peak. Right, so in going from 44 to 29, a methyl piece has been removed. In going from 44 to 15, an ethyl piece is removed. We put the two together, ethyl with methyl, we get propane. This is the fragmentation pattern for ethanoic acid, carboxylic acid. We'll just have a look at the structure of that, change the colour again. Ethanoic acid is CH3, COOH. Right. We can predict where fragmentation might occur. It might happen let's say, at this point. Right, so that would mean that this hydroxyl group would be removed, and hydroxyl groups, again, are a familiar number of a weight of 17, and we can see that the separation here from 60 to 43 is 17, so that corresponds to the hydroxyl group. These numbers, by the way, that are listed here are numbers that have come directly from the IB syllabus. So these are characteristic numbers that you should memorize, that will pop up in spectra frequently. And so we've already seen the 15 for the methyl group and the 29 for the ethyl group. The 29 really could be the molecular weight of any number of things. The ethyl group is most common, but the aldehyde group, CHO, is also another very common component or fragment that weighs 29. Alright, what else? If bombardment occurs there, we would knock off a methyl group, so that has a weight of 15. We can see 15 in the spectrum. We can also see a separation from 60 to 45 of 15. So this would mean that this 15 piece stayed in the mass spectrometer, and the 45 fragment has come through. So the 45 fragment would be the carboxyl functional group as an ion. And so looking at the fragmentation patterns, we can see things that are present in the molecule, pieces in the molecule that can be put together to give us an idea of the overall molecular structure. So yes, if you are asked to identify each of the fragment ions or each of the ions in the spectrum, you must remember to put the positive in the structure. So this is the molecular ion peak. The weight of acetic acid or ethanoic acid is 60. Then that 45 is the carboxyl functional group. That piece is the leftovers when the hydroxyl functional group is removed. And then we've got the methyl fragment ion that's come through. Okay, so that's mass spectrometry. Now you can practice your skills by going through some of these questions and see if you can apply your knowledge to these questions.